Okay, I want to show you one more cool and useful technique here during the transform data task of the data preparation phase. I want you to save that experiment we were working on in this video, and we're going to come back to that and continue on with that when we get to the simplified data task down here. But for now, I want to show you one more technique using apply math operation again. That's going to be very important for the later modeling phase. Anyway, make a new experiment. Let's call this one feature engineering for nonlinear relationships. So I have the import data pill. I'm still working with the same, no, I want to take a break, and I want to, instead of using the, what do you call it, the lending club data, let's go back to bike buyers again. So import data, same database we've been using all along. However, we're going to select all from bb_bike buyers this time. Make sure you cache the results, get that running. The idea here, while this is running, I want to show you in the bike buyers data, and this is the same data set I've been using in prior examples in the book. So if you have this, pull it up. If you don't, I'll include it as a link there right next to the video that you're watching in the book. But I want to show you something we do to prepare the data for nonlinear relationships. So in the modeling phase, particularly when we use the multiple linear regression as a modeling technique, which I know you haven't done yet, but you'll learn it. Some of these techniques, these algorithms, assume a linear relationship between every independent variable and the dependent variable. So let me give you an example. Our dependent variable is purchase bike numeric, and in this case it's coded as a 0 or 1, which is why we can use multiple linear regression. It's numeric. However, we have other numeric variables, all of these right here, that in the data understanding phase we created visualizations to look for clues about variables that might be related to purchase bike numeric. So let me give you one example. Let's do income. No, let's do age. No, I want something more continuous. Let's do age and income as our first example. I'm going to insert a scatter plot. So you can also do this in either Tableau or Power BI if we've been using those in class. They'll both give you the exact same options to do what I'm doing right here. Anyway, here in this scatter plot, we have income on the bottom, age across the top. Cool, that makes sense. We get it. The reason why these are grouped into these bars like this is because income is rounded to the nearest 10,000. So age is only plotted across 10,000, 20, 30, 40, and so forth. So looking at these plots, do you see a trend? Well, it looks like it goes something across here like this, but is that line angled? And we call it a trend line. Let's go ahead and add the trend line. And although we don't have a lot of time in this class to get into the math behind this line of best fit or regression line or trend line, what it does is this is the line that minimizes the sum of squared residuals between each plot and the line. So we take the difference between this point and the line, and we square it to get rid of the negative sign, because down here the difference between the line and this dot down here is negative. All these dots above it are positive. What we want to do is just get the actual distance from here to here represented in a positive number so that I can compare dots above and below without one being positive and one being negative. So that's why we square it. And by squared residual, I mean the difference between that dot and this point, the residual. So this line, the idea is we want to draw a line that perfectly fits each of these dots to represent what's going to happen, because that way we can predict. I can say, okay, I don't have anybody who makes 140,000. As you can see, there's no dots. But because of this line, I can predict that anyone who does make 140,000 is going to be 50 years old. That's the idea of a trend line. Now, this line is straight. It's an assumption. We assume that the line is straight. But is this line coming close to touching every dot? No, not at all. And so a straight line isn't the best assumption for how this variable is related to that variable. In truth, there's a lot of variance going on here. So what we want to do is create some alternate versions of these variables that don't depend on this relationship being straight. Now let me show you what I mean. Let's add some components here. Oh no, we already got the trend line. Click on the trend line if you're in Excel. If you're in Tableau or Power BI, you'll be able to do this same thing. It'll show you some formula. So I've selected the trend line. I'm going to right click and go to Format Trend Line. And it gives me these options here. It says, okay, right now your line is linear, meaning it's straight. But you can do a few things with this. It can be exponential, which means it allows the rate of increase to increase. See how the slope is increasing as we move along? That's what we mean by the rate of increase increasing. Logarithmic's the opposite. The rate of increase decreases. Polynomial means we can have these inflection points where it changes from up to down to up to down. And we can have as many inflection points as we have order over here. This 2 means that it can go up once, down, and then back up again. There's 2 inflections in that. I'm going to ignore power moving average for now because these 4 are the ones we're usually working with. So how do I tell which one's the best? Well, that's what we do by coming down here and clicking on Set Equation in Chart and Display R² in Chart. So I don't believe we've gotten to R² yet in this class, but we will. We have covered correlation, a Pearson correlation, which is R. R really is just, R² is just R². And what it does is it represents the amount of variance in the y-axis variable that's explained by variance in the x-axis. So as this goes up, to what degree does age go up as well? So here it says 0.045, and we interpret this as a percent. So that means 4.05%. So income explains 4.05% of the variance in their age. It's a pretty small number, but relatively speaking, this could be one of the best numbers. So linear, original one, was 2.86%. That was even worse. So by going to exponential, it says, yes, there is a tiny bit of curve up, like this image implies, although we can't really see it because it's so small, but our R² improved. That means that this exponential line is better than the straight line at describing the relationship between these 2 variables. So that's why we pull in the trend line. Visually, it's tough to see that there is this exponential thing happening because it's so subtle. So if we know that exponential is better, then if we do the opposite, we know that logarithmic should be worse than a straight line. Yep, indeed, it goes down to 0.0246. However, there's still a chance that polynomial could be better than both. Nope, it's actually not. So for these 2 variables, exponential is the best way to represent it. All right. Now that I've explained the concept, how are we going to apply this to this data set? So we only care about our dependent variable. All right, I'm not trying to explain or predict age. I'm trying to explain or predict purchase by numeric. So what you should do in the data preparation phase is take each of your numeric independent variables or features, scatter plot them against the label, examine the trend line, and see which nonlinear transformation is best to represent the relationship between each one of these and the dependent variable. So let's start with income. Actually, no, I like age, and I'll show you why. This one's, no, I'm going to stick with income. I'm going to show you 2 of them. So purchase by numeric and income. Let's insert a scatter plot. And here, because purchase by numeric only has 2 values, 1 and 0, it's even harder to look at this and have any clue what the relationship between these 2 variables are. We have to add a trend line to see, because remember, this dot, I don't know if this is 1 dot or 100 dots that are all right here because they're all overlapped. And I don't know how heavy any of these are. I think Tableau does a better job in Power BI of shading these dots so you can see where there's more or fewer. But anyway, add a trend line. Okay, yep, we got a positive relationship. That means as income goes up, generally speaking, their likelihood of purchasing a bike goes up. It shifts from whatever this is, 0.048 up to 0.55 or something like that as I make more money. But we don't know if a straight line still is the best way to represent that. This isn't wrong, the straight line. It is true. Over all of our data set, there is an increasing relationship. But we don't know if it's consistent across all values of income, as a straight line would indicate. Is it truly always the same increase from one unit of 10,000 income at a time to the next? Maybe, maybe not. So come over here. It doesn't even give us the option for exponential. Why? Because exponents don't work with 0 values and are variables between 1 and 0. So you might actually choose to scale. You could change purchase by numeric to 0.1 to 1.1 or something like that. But I think it's actually going to be better to let's not worry about that for now. Let's try logarithmic. So to know which one's best, remember we got to add our display our equation. The equation we're actually going to need later for understanding how to transform. However, we definitely need R². So the relationship here, the linear relationship between these 2 variables is terrible. Income does not do a good job of explaining whether or not they purchased a bike. So let's change it to be logarithmic. All right, that's better. It went from 0.001 to 0.003. But let's see if polynomial is even better. Nope, it got worse. However, we can try various orders of polynomial. 0.006, that's the best we've seen so far. When I go up to 4, it goes only to 0.0063. At some point, especially with these polynomials, you've got to, we don't want to keep adding complexity to our model. Adding a fourth, so the cube term did not really help the r squared much. So you can see this is our y equals mx plus b formula right here. I'll get to that in just a minute, but what I want to do is come back here and say, okay, 4 is too many. I've never done more than a cube term. When I go above a cube term, it just starts to get too complex. And we increase the chance of overfitting our model, but we'll talk about in the next chapter. For now, just know that, okay, this is our best relationship. Let's do one more. Let's do age, because this one has a cool story to tell. Let's grab age and purchase by numeric, insert a scatter plot, add a trend line. Okay, and this appears to go down. So as people get older, their likelihood of purchasing a bike decreases. This is the steepest line we've seen yet. So you might think, okay, we got to target all younger customers. Is that the conclusion? Well, that would be a bad conclusion. Often, I'd say more often than not, the straight line is actually not the best representation of the data. It sometimes is, and when it is, that can be pretty powerful, but usually it's not. Usually there's going to be some nonlinear transformation that's better. Anyway, let's take a look at our options here. Logarithmic, first add the r squared in the equation. Let's move this up. Give ourselves some room. We're going to need this room later. All right, r squared, 1%, 1.13. Let's change it to logarithmic. Gets worse. So definitely not a steep downward trend. Let's go to polynomial. All right, interesting. Now this one, it improved it over doubled from 0.01 to 0.02. So what it's saying now is that as people get up to age 40, they're more likely to purchase a bike, but then they get much less likely to purchase a bike. Okay, let's go as high as a cubed term, but that's it. Look how much it changed again. So people get more likely to purchase a bike till age 40, less likely of purchasing a bike until age 74-ish, and then much more likely to purchase a bike to 90 or 89, whatever that is, 89. Okay, and our r squared increased again from 0.01 to 0.02 to 0.03. If we go up to 4, no, not good enough. Right here, the increase, notice the increase went up to only a little bit better. Let's stop right there. So we've determined that the relationship between these two variables, purchase bike numeric and age, is not linear. In fact, it's polynomial with a cubed and a squared term. How do we then do something about this or create a new variable? All we have to do is look at this and know that a cubed term and a squared term matter. Now in the next chapter, when you learn about regression, you're going to see how this formula turns into a prediction. I don't want to get into that level of detail right now. All I want you to know at this point is that this x term represents age. And this number in front of the x term represents how important age is in determining income. So if I just take age as it is, it's got a weight of 0.1473. If I square age, that means if I add an inflection point, there's an additional weight of negative. See how it goes down right there? That's what we mean by negative. Negative 0.0029, which doesn't sound like a lot, but remember that gets squared. And then there's another weight, a positive one, see it going back up here, for a cubed term of age. All I have to do now at this point is recognize that I need to add up. This x means age. I've already got age in my data set. I now need to add a term for age squared and age cubed. I know you won't understand how it's used yet. Just know that's all it means. I've got to go in here and add 2 more columns, 1 squaring age and 2 cubing age. That's all this means. So what I'm going to do now is go back to my experiment. Let's see. Let me re-enter my credentials here and make sure this is all working. Okay, that one should be fine now. Let's grab an edit metadata. Whenever I'm doing these math transformations, I don't always need it, but it helps just to be safe to grab an edit metadata, and we are going to make sure that age is an integer. right there. So we're going to say, just in case in the original data set it was not stored as an integer. Plus, since we're importing data from another database, what if that database administrator changes the age data type to text for whatever stupid reason? We can't control that. So it's good to have edit metadata to just go ahead and say anything that's supposed to be an integer, let's cast it or force it to be an integer data type once it gets here. So let's run this, get to that point, and then let's make our transformations. Okay, so let's make sure we are all on the same page here. Let's visualize what's coming out of metadata. It's the original data set. It looks just like the original. The only thing that's changed is that we've forced age to be an integer column, at least internally to Azure Machine Learning Studio. It now knows for sure that age is an integer. That's all that we did here with edit metadata. So next, let's apply a math operation. Now we can actually do this a few ways. We could use a SQL, apply a SQL transformation, which you'll learn later in this chapter. That would work as well, but let's just use this one. So this says, all right, we've already looked through it. We've got all these different options. I think what we want is, no, we don't want to compare. Basic? Yeah, I think what we want is basic. So we need a squared term first and a cubed term. That's what we learned from this r squared being the best. It means in our formula here, we already have age in its current form represented as this x. This negative 0.1.8 is the intercept. We're not going to worry about that for now. It's or error. We have the regular term. We just need to add a term for age squared and age cubed. That's what we're doing. So basic, I think we have a squared. Here it is. I think this will do it. So let's select our column. Age, already in there. Oh yeah, I added it previously. Good. Output mode. Remember, result only means it's just going to return age. No, I want all my data. So append it. I don't want to do it in place because it'll replace the original age column with the squared version, but I actually need both. According to that formula in Excel, I need all three terms. So I'm going to append this. Looks like I can't rename it, but that's fine. Let's go ahead and run this one. All right, that was nice and quick. Let's take a look. Visualize. Okay, so I still have age right there, but at the end, there we go, I see square age squared. So now all I need is age cubed. All right, I don't think there was a cubed function, but let's grab another apply math operation. Copy, paste. Okay. This time we're working with, is there cubed? Let's see, not cube root, exponential, exponent, raised, it's one of these. Hold on, let me look it up quick. Okay, found it, I should have known better. Power, there we go, power. So we're going to say take age and raise it to the power of 3 to make a cubed version. And I could have done the same thing with the squared as well. I could have just raised it to the power of 2. All right, let's add that one then. We're going to append it. Yep, that looks good. Run selected. Let's see how long this takes. Pause. All right, that's done. Let's take a look here. Okay. We still have all the data because we used append. We have the squared age from the previous one and the cubed age from this apply math operator. Now, as you can see, once you start raising to the squared and cubed power, these numbers get big really quick. So if you were to do this with something like income, these numbers would be gigantic. So what you can do is before you even create the squared and the cubed term, you could go back to the original variable, let's say it was income, and I would divide by 10,000 or something like that. That still maintains the spread of income and the scale, but it just well, it maintains the spread, but it'll just reduce the scale down to something much smaller so that when you make that squared and cubed term, you're not dealing with such large variables. So this is also an example of feature engineering. And in particular, it's how we deal with nonlinear transformations, which are represented easily when we go and create scatter plots during the data understanding phase. So during that phase and data understanding, I would actually you could make this task part of that phase and report it on your data exploration report. That'd be fine. You could also do it just during this phase as well, and then use this to document, here's why we created a cubed term and a squared term to represent this nonlinear effect that's happening right here. So now what I want you to do, save this experiment now that you get how to do this, and let's go back to the previous experiment you were working on and continue along where we were learning before with the simplified data task.